So the topic of my talk is essentially observers in quantum mechanics. This isn't really a work in progress. It's not even a work prior to progress. I just took the we had some funding under the topic of observers in physics, or the physics of observers, I think it is, one of the two. So this was actually an opportunity for me to revisit some of the things that first got me interested in philosophy of physics. As an undergraduate in Bristol some years ago. There's going to be nothing particularly novel here, though hopefully there'll be something that will be somewhat new to everyone, probably different things. It's going to be essentially conceptual rather than technical. I don't have any equations on the slides, although I might have to put some stuff on the whiteboard. It's late in the afternoon, you've had a full day of activities, you probably just want to sit back and noodle around about quantum mechanics, so we'll try and enable that. So the outline of the talk, I'm going to do a sort of historical introduction, trying to tell the story of how observers came to be left out of quantum mechanics, concentrating on Heisenberg. I'm then going to perhaps introduce a sort of atypical way of motivating the need to include observers in the theory, namely Howard Stein's notion of the schematized observer, which will hopefully bring out a couple of things that I think are important sort of desiderata on whether this has been successfully done. My main sort of case study is going to be the observer in Everettian quantum mechanics. That's going to be the topic of most of the talk. So I'll go into some depths about problems and potential resolutions and potential worries and so forth. The one thing that was sort of new to me in coming across for this talk was Zurek's quantum Darwinism, which I think will be relevant perhaps to some of these worries that I'm going to raise, so maybe that'll be one thing that's new to you at least. And so that's sort of where I'll rest, which brings us pretty much up to the minute with research in these kind of topics. So that's the plan. I'm starting with Heisenberg in 1927. As far as I know, this is the first place where you really find expressly this idea that quantum mechanics is sort of a theory of what we can observe. It's not really a theory about that includes us in it. We're sort of an illegitimate subject matter to the theory. So in Heisenberg's 1927 uncertainty paper, there's this interesting remark. I believe that one can fruitfully formulate the origin of the classical orbit in this way. The orbit comes into being only when we observe it. And to sort of contextualize this, the old quantum theory was a sort of semi-classical theory, and the discontinuity was between these stationary states, which could be associated with classical orbits, and it's classical trajectories for some kind of particle, what have you. With the development of the new quantum mechanics in 1925 through 1927, it became a lot less clear that the states of a hydrogen atom, say, could be associated with anything like definite trajectories, and Heisenberg is trying to give an account of the intuitive content of the new theory of matrix mechanics, and he says that this is the way that we can think of orbits in the new quantum mechanics. Generally, we're going to have superpositions of orbits, but when we look, we see a definite property of the system, a definite orbit. And there's something about what we do to the system that is important. And so in the official conference proceedings of the 1927 Solvay conference, we have Dirac preparing some remarks about the measurement problem, saying that, well, at a certain time, sometimes the dynamics leads to the state of the system being expressed as this sum of this decomposition into the superposition of different components, and nature chooses one of those components at that time. So in his comments, Heisenberg says, I do not agree with Mr. Dirac when he says that in the described experiment nature makes a choice. I should rather say, as I did in my last paper, it's unclear exactly what he's referring back to, but perhaps something like this. That the observer himself makes the choice, because it is only at that moment when the observation is made that the choice has become a physical reality, and the phase relationship in the waves, the power of interference is destroyed. So there's something happening when an observer makes a measurement, when an observer intervenes on the system, that changes somehow the quantum state. And this idea, I've got, oh no, you could also talk about the origins of what's sometimes called the Heisenberg cut in Heisenberg's work, but the sort of best expression of this idea is actually by von Neumann. So here there's this idea that in giving account of measurement, we can cut up the systems in different ways. We've got the object system, the thing we want to measure, with the apparatus and the observer, and we can move our application of claps between those systems. It doesn't really matter as long as we do so, as long as we apply claps before we get to the observer. So here's what von Neumann says anyway. No matter how far we calculate, to the mercury vessel, to the scale of the thermometer, to the retina, or into the brain. So he's thinking here of a typical classical experiment. We're just going to measure the temperature with an ordinary thermometer. Still, even there, at some time we must say, and this is perceived by the observer. That is, we must always divide the world into two parts, the one being the observed system, the other the observer. In the former, we can follow up all physical processes, in principle at least, arbitrarily precisely. In the latter, this is meaningless, and the boundary between the two is arbitrary to a very large extent. So he's trying to say that there's this general moral about measurement in physics, namely that measurements are ultimately the result of an observer's noticing something, and there's going to have to be there's a sort of a parallel description in the physics, but at some point you're going to have to say, here's the observer, here's what's happening in the physical world, there's a split between them. So applying that back to quantum mechanics, he says, quantum mechanics describes the events which occur in the observed portions of the world, so long as they do not interact with the observing portion, the observer, with the aid of process 2. He's got this distinction between the unitary evolution given by the Schrödinger equation and process 1, the transition to a mixed state, that is collapse. So we describe the event with the aid of process 2, that is unitary evolution, but as soon as such an interaction occurs, i.e. a measurement, it requires the application of process 1, collapse. The dual form is therefore justified. However, the danger lies in the fact that the principle of psychophysical parallelism is violated so long as we've not shown that the boundary between the observed system and the observer can be displaced arbitrarily in the sense given above. That is, he has shown that, so we don't need to worry about the psychophysical parallelism. Because we can displace the border arbitrarily right up to the observer's brain, retina, brain, what have you, right down to the atomic system, somehow that arbitrariness speaks to the sort of, in one sense it's necessary. When we've got an observer, we need to have this split. In another sense, it's arbitrary, and the arbitrariness says that there's nothing physical that this corresponds to. It's just something about the nature of what it is to make an observation. As I mentioned, sometimes get called the Heisenberg cut. There's a good reason for that. You can read about some of that in epistemological and but of course, we have to draw the line. This gets expressed in various ways. The reason for this gets expressed in various ways. We have London and Bower in 1939 talk about the self-knowledge of the observer. We have this special relationship to one kind of system, namely ourselves, and we have this this sort of intrinsic self-knowledge, and that gives us a right to create our own objectivity. What we know to be true through introspection must be true. We have the right to say this is the way the world is. The right to apply claps. And then Wigner in this famous paper, famous mainly for Wigner's friend, this fun paradox, which is much like Schrodinger's cat, but you replace the cat with a conscious observer. You can then ask what they experienced when they looked at the result of a measurement. It's famous for that. It's infamous for his contention that there's this special property of his friend, namely consciousness, that means that the principle of charity. So this is sort of extending self-knowledge to other people through its principle of charity to say, well, if this other person says that they experienced a definite result, then I should believe them. It would be uncharitable of me to think otherwise. So why might that be a point at which I had to apply claps? You know, if I got a machine there, I wouldn't have applied claps. I've got a person there who can describe to me the experience. Well, it must be because they're conscious. So it's the sort of notorious part of the paper. So, I mean, it's interesting that these are sort of epistemic arguments in a way. We're talking about self-knowledge, we're talking about principles of charity. But the conclusion that you can draw from these sort of considerations is that, well, an observer can't exist in a superposition, and if quantum mechanics is to describe observers as doing such, well, then it just doesn't apply to observers, it only applies to the observer system. So, whether these propositions are convincing, there's certainly a lot of people that they haven't convinced, but it does seem that there's only a few places where you find these sort of sentiments being expressed explicitly. I haven't gone into Niels Bohr because I think things are a bit more complicated there. But you know, these are physicists self-consciously trying to say what it is they believe the Copenhagen interpretation. That's a bit of a contested term, but what that amounts to, whether or not they believe in their heart of hearts what they're saying, that sort of attitude did prove useful. Why? Well, at least this idea that the observer sort of has this special power. You can choose to go and look at a quantum system and collapse the state. And that idea was important to some important foundational works in quantum theory under the rubric of the operational approach. So Mackey's formulation of quantum observables. So he was a mathematical physicist doing important technical work, but the interpretation he gave his work was when you decompose an observable into projections, what you're doing is representing the possible experimental questions that an observer, an experimenter, could ask of the system. And formally, when you look at how that's represented within the theory, well, you just have a free choice of which question you want to ask, when you want to ask it, and the theory spits out the probabilities for a yes or no answer. This was in the 50s. A bit more recently, a few people helped develop this standard model of measurement, so-called, according to which slightly more generalized kind of quantum observable. So we were talking about projections, projection valued measures up here. Today in quantum information theory and so on, we talk about positive operator valued measures. The distinction is essentially that with a projection, you have a spectrum that's just 0 and 1. With a positive operator valued measure, I mean the values that measure takes, the positive operators, they have a spectrum that is some subset of, some measurable subset of the unit interval. So sometimes they are called fuzzy observables. Anyway, the important technical result is that this sort of Mackey-style understanding of quantum measurement is sufficient to measure these more generalized observables. You only need a unitary interaction between the system and apparatus, and then projective measurement of a PVM on the apparatus by an observer, applying the collapse postulate von Neumann's process 1, and that there's always that PVM in the apparatus and a unitary evolution that interacts the two, that enables you to measure whatever you like on the object system. And these developments are closely related to more recent informational approaches to quantum mechanics. At one point I was going to talk about those, but I decided not to for reasons of time. So just briefly, you might see the sort of modern heirs to Heisenberg's thoughts about the observer being outside the system in something like quantum Bayesianism or cubism. They've decided to dub it these days, because it's not really Bayesianism, it's more sort of De Finetti style subjectivism. And there you have people saying like the quantum state is just a collection of degrees of belief about, say, possible measurements we could do in a system. So to say that an observer is represented by a quantum state on that sort of view seems like a category mistake. An observer isn't a collection of degrees of belief about possible measurements. So of course you might attribute to an observer a quantum state, but that's, it's not going to be, you're not going to want to say that an observer is a quantum state. Anyway, but if people want to bring that sort of thing up, I'd be happy to talk about it. So that was a sort of introductory part about how quantum mechanics came to leave out the observer, and how it wasn't a terrible thing for the development of the theory. One reason you might be unhappy, though, with the operational approach is that it's associated in philosophy of science with instrumentalism, and perhaps you don't like instrumentalism. For the instrumentalists, successful theories are something like tools used to predict and systematize experimental data. But the sort of worries that people have about that view are things like we use even if our theories are tools, even if they're instruments, we use those theories to do far more than just predict the results of experiments. Quantum mechanics explains the spectrum of solar radiation, the specific heats of solids, the stability of matter. It seems like those sort of considerations are relevant to much more than just these very limited laboratory experiments. So those sort of considerations might lead you down the path to scientific realism, this view that scientific theories, successful scientific theories at least, do truly represent reality in some sense. But you might first ask a sort of, in a way, a more fundamental question. How does a mathematical theory, you go to a quantum mechanics textbook, tells you about Hilbert spaces, self-adjoint operators, and so on and so forth. How do those things come to be about the world at all? It's mathematical objects when you read them in a textbook. So I'm not going to try and do justice to the dialectic of Stein's paper. I'm just going to give a few choice quotes. So Stein says here, I suggest that the principal difficulty is not that of how to leave the theory outside the laboratory door. Here he's referring to the theory-ladenness of observation. That doesn't worry him. But rather that of how we get the laboratory inside the theory. It's a bit of an odd thing to say. Well, how do we do it? For of course we do put theory and experiment in relation to one another. Otherwise it would be impossible to test theories and impossible to apply them. Okay, fine, that's an operationalist. But, says Stein, it would also, I should add, be impossible to understand a theory as anything but a purely mathematical structure. Impossible, that is, to understand a theory as a theory of physics if we had no systematic way to put the theory into connection with observation, that is, experience. So his solution to this problem, he says, where Kant speaks of schematizing the categories, the manifold of intuition, I want to speak, as it were, conversely, of schematizing the observer within the theory. But the intention is analogous, to secure empirical content within experience for an abstract structure. Fancy talk, but a simple idea that will be found perfectly familiar. One represents the observer within the spatio-temporal framework by a world line, or a system of world lines. So that's what this amounts to. So just some thoughts about that. So for Stein, what it is for a physical theory to be successful, he's not necessarily a realist in the traditional sense. He says a successful theory of physics represents the mathematical structure discernible in the world of phenomena, of observations, of experience. So by schematizing the observer, that is, ourselves, we describe experience in theoretical terms, and we're able to recognize in experience, our experiences, the structures described by the theory. Did I get? Yeah, I didn't. Okay, good. So there's more going on than just declaring that the theory represents the world. There's a sort of a necessary condition for injecting empirical into the content, into the theory. We need to be able to see that we can put ourselves inside the theory and then recognize what we do in fact experience as being described truly by the theory. So for Stein, this replaces the old logical empiricist view that empirical content comes from having an observational vocabulary, which is antecedently understood as being about everyday objects and so on that we use in everyday life to describe the world. For the logical empiricists, we express the consequences of the theory in terms of this observational vocabulary and our sort of pre-existing understanding of that language sort of that secures the aboutness of the theory. It gives empirical content within experience to the theory. So, no one's a logical empiricist anymore. They're relevant. But this requirement on a physical theory is, in a certain sense, more stringent than that required by realism. So, because I'll talk about him later, here's David Wallace describing the sort of realist he is at the beginning of his book on Everettian quantum mechanics. Says, ever since Newton, physicists have been in the business of constructing mathematical models of aspects of the world. Models in the sense that they are, or are intended to be, isomorphic to the features of the world being studied. So classical n-body mechanics, for instance, describes the movement through three-dimensional space of n-points, and claims that the movements of real physical particles are correctly described by the movement of those n mathematical points. So here there's no reference to experience, no reference to conditions to make this abstract structure about the world, other than intending it to be about the world. That seems to be sufficient in this quote for sort of securing reference to the world. So Wallace is a structural realist, so he doesn't want to say that it's the terms of the theory that instead he says that the models of the theory are isomorphic to the features of the world being studied. So the thought is that through schematizing the observer along Stein's lines, Hal Stein's lines, there's a requirement that you need to do more than just declare this theory is about things in the world, unobservables, sure. It's not that the theory can't be about unobservables, but yet there's this requirement that certain structures within the theory should give us a way to place ourselves within the theory and discern in the world of phenomena, of observations and experience, those theoretical structures. And interestingly, at the end of this paper, Stein says, well, what about quantum mechanics? And well, we'd like to say a similar thing about quantum mechanics, particularly in respect of what it tells us about the structure of causation and our intuitions of causation. I'm not entirely sure why he brings in causation in this. Anyway, but this we cannot do. In this theory, we just do not know how to schematize the observer and the observation. This is a quick way to characterize what I regard as still the basic unsolved philosophical problem of interpreting the theory. In other words, here the difficulty of getting the laboratory inside the door of the theory is of a new, and I think still not understood, order. And I should say that Stein, in his philosophical work on quantum mechanics, developed the operational accounts probably more fully than any other philosopher of physics. So it's not that the problem is representing experiments and the results of experiments in theoretical terms. He thinks that the operational account of Mackey is quite adequate to do that. It's this second thing of placing ourselves within the theory so that we can identify in theoretical terms the structures discernible in our experiences and see those matched in the theory. And that for Stein is what allows us to say that we understand the theory as a theory of physics. Yes?
So the way you've set it up so far, you've kind of set it up as if Wallace doesn't recognize this as a goal of interpreting quantum mechanics. And maybe that's something you're going to address further down the line, but that's not my thinking about what's in the book, it seems like he does do things to address this kind of question, right?
Yes.
This is kind of a question of, yeah, okay.
Yes, I'm going to come back to Wallace.
Okay.
So I'd just been reading this passage. So I chose this as a neat expression of what realists tend to say. If you and structural realists in particular, if you look at Ladyman and Ross, when they talk about the relationship between theoretical structures and the world structure, they just say, well, there's this relationship of representation. We can't say anything more than that. We can't, asking us to get beyond our description and get at the real thing is just, a sort of mistaken demand, or an impossible demand. All we have is our theories, our language, and to sort of bridge the gap from that to the structure of reality is a sort of
but there's also this kind of point in philosophy of science, I think, Callender and about the question of the problem of representation in philosophy of science. The point's not that we can't say anything more about representation and the nature of intention. It's that for certain questions we're interested in answering, we can postpone that question. I think is maybe the attitude.
Yeah, so I
don't know.
I'm not trying to say that there's necessarily something problematic about the idea that we use theories to represent the world. What I'm trying to draw attention to is Stein's different perspective on the way that theories come to be about the world. Namely, that there are certain definite requirements that we might have. I mean, that go beyond just saying, well, I can use what I like to represent what I like. I just have this sort of ability to. So I'm thinking in the background here of Van Fraasen's account of representation, which is essentially pragmatic. And just says, look, well, we just have this ability to take one thing to stand in for another thing. We represent it, thus and so. There's nothing that mysterious about that. What is mysterious about Fraasen is the claim of isomorphism. So, I think all I've done is muddy the water there. Perhaps the best thing is just to go on and then we'll come back to this. The reason I introduced this is because I think it gives a better characterization of what success would look like for a representation of the observer within the theory. And I've not yet said that Wallace doesn't have the resources to successfully do that, or that his realism counts him out from doing so. Okay, so moving on to Everett. This is going to be my case study, and perhaps one of the things that Stein has in mind when he says we just don't know what it would be to. We don't know how to represent the observer within the theory. Well, why would you say that? Well, because things kind of seem to go a little haywire when we try to. So, going back to Everett's original paper of 1957, we have. So, just read out a few quotes. Well, maybe this would be a good opportunity to draw something on. So, we're just doing the sort of hoary old intro to philosophy of physics account of the measurement problem, where let's say we've got some state of qubit, say, properly normalized. And we want to represent the measurement within the theory. So we've got a quantum state, we've got an apparatus ready to go and record the results of measurement, and we've got our observer. The measurement interaction, unitary interaction, if it's going to be sufficient to give us information about the state, it's going to be unitary, it's going to be linear, and so when we expand this out, so my size of writings. So our apparatus is going to record 0. Maybe we'll have an observer raising their hand like that. So that's now tiny. So nothing. No, wait, it's the same one. Doing that. So the thought is that I can't at the same time both raise and lower my head. That's going to represent my experiences being distorted. Okay. As a result of the measurement interaction, the state of the measuring apparatus is no longer capable of independent definition. It can only be defined relative to the state of the object system. In other words, there exists only a correlation between the states of the two systems. So the idea of the relative state is that relative to the state of the object system being 0, the state of the measuring apparatus records 0. I raised my left hand. Relative to the state of the object system being 1, the state of the apparatus reads 1. I raised my right hand. And if I'm concerned with describing the experiences of the observer, well then it's the relative state I should be interested in. So maybe I've done that too early. We have the task of making deductions about the appearance of phenomena to observers which are considered as purely physical systems treated within the theory. We arrive at the following picture. Throughout all of a sequence of observation processes, there is only one physical system representing the observer, yet there is no single unique state of the observer, which follows from the representations of interacting systems, two relative states. Nevertheless, there is a representation in terms of the superposition, each element of which contains a definite observer state and a corresponding system state. Thus, with each succeeding observation or interaction, the observer state branches into a number of different states. So the idea here is if we introduce another system, run all this again, then this relative to these states, we will get a further two branches, a further two relative states. Relative to these, we will get a further two states. So there's an ambiguity here about what is doing the job of representing an observer within Everett's account. So, and this is nothing original at all. So Everett identifies an observer with a physical system, but then identifies the experiences of an observer with a relative state of that system. So we can, if we have if my qubit is a vector in H1, the initial state of the observer is a vector in let's call it HO, as is each of these, and indeed just the position of these two. The observer, which I'm calling observer S, so I should call this S, is being thought of as somehow being the physical system whose state is being represented by a single vector here. And the second is the relative state, which is relative to a term in this superposition. So in that case, it's true to say that the state of the observer identified with the system that sort of doesn't branch, the system just is itself all the way through. That system is in a superposition with respect to these two states. Nonetheless, the relative states correlate with a single measured value, namely this. Now, since we experience definite results, it seems like we are these observer R's, the relative state observers. If we want to pick out our experiences within the theory, we don't seem to have these superposed experiences. I don't find myself at the same time raising and lowering my arm, that sort of thing. But if we're really to be identified with the observer S, the superposed observer, then our reports about our experiences are radically mistaken. You know, we can continue this sequence where we go and talk to our friends, tell them what we saw in the lab, so on and so forth. So an observer R will report that they saw a definite result, but for the observer S, there was no definite result. The experience of an observer is disjunctive, so I'm using Barrett's phrase there. And Barrett goes on to accuse this bare theory account of Everett of what he calls empirical incoherence. So he says that there's this necessary condition on accepting a physical theory on empirical grounds, namely explaining how, if it were in fact true, one might have empirical justification for accepting it. So such a theory is empirically coherent. If a theory fails to be empirically coherent, it might well be true, but if true, then one could never have empirical reason for accepting it as true. In this sense, a theory that fails to be empirically coherent could not be an object of scientific knowledge. So if you're wondering where Nick and Chris get their notion of empirical incoherence from, it comes from Jeff Barrett. So he says the bare theory fails to be empirically coherent since it predicts that one would almost never be in a position to determine reliably the nature of one's own experience. Thought being that if we are in fact the observer S, if Everett has really identified observers with the system that exists in the superposed state, then believing the reports of the observer R's who are inclined to say that they experience a definite result, is to falsely believe that they do have definite experiences, when in fact they're having these disjunctive experiences truly, according to the theory, and so we're being radically misled. So, I mean, it seems to me that that's pretty clearly not what was meant, and the response of Everettians has been, it seems, to try and find a way to justify the claim that as we represent ourselves in Everett's theory, we must do so as the observers in the relative states. So in the 1980s and 90s, it was thought that this required adding something to the theory, specifying a set of branching worlds that was known as many worlds, or specifying a set of dividing minds, saying, well, there's a mind in each of these relative states, and as we do further experiments, we get more minds, and what we need to explain how our theories, our experiences can be determinate within this theory is to show how we can give an account of these many minds, each of them corresponding to definite experiences. So the suggestion there is that the bare theory is inadequate if you just take quantum mechanics, subtract von Neumann's process 1. Yeah, subtract von Neumann's process 1, you get quantum mechanics without collapse. If you want to secure definite experiences for your observers, then you had better add something to the theory, a set of worlds, a set of minds. Everettians today reject that idea. And in particular, I think we can pick out an Oxford contingent of Everettians who've been at the forefront of taking this sort of line. So, looking back to Simon Saunders, I think you can trace this back to his 1993 papers, one of which I suggested as reading, as saying that the theory doesn't need addition of this sort. Important to that claim is decoherence, which I'll come to later, but there's also this idea that, and he develops this in a series of papers, all of which have time and quantum in the theory in various orders with various other things going on. But Saunders argued that, by analogy with the B theory of time, that is the theory of time that rejects the present, past and future being meaningful predicates that you can apply to events. The B theory instead looks to temporal relations like earlier than, later than. Those are relations that don't change, whereas the past, present and future change depending on which events are present. McTaggart argued that led to inconsistency, led him to reject the reality of time. B theorists say that, well, what we should hang on to are these objective temporal relations. These are relations that don't change, and then by understanding the present relationally, understanding an event as being now, to the extent that we see ourselves as presently being contemporaneous with that event. That's not a sort of nonsense thing to say. So by picking out a time as now, we can then fill in the past, present, and future just by looking at the B theoretic relations. The future is all the events that we are earlier than, and that passes all the events earlier than us, and then there are events that are neither earlier than nor later. That's the present. So Saunders argued that the actual, like the present, should be understood relationally in Everettian quantum mechanics. And he also claimed that by an analogy to inertial frames in Minkowski space, that all bases of Hilbert space are metaphysically apart. So there's this traditional problem for Everett, namely the preferred basis. As I've written it out here, there's this nice decomposition into two definite stories, but a vector state is a basis-independent mathematical object. I can write down the same vector in whatever basis I choose. So traditionally a problem for Everettians was, well, there must be a preferred basis with respect to which the decomposition leads you to this picture of many distinct, definite worlds. So in a sense, he just concedes that point. He says, well, metaphysically speaking, yes, all bases of Hilbert space are metaphysically apart. There's nothing to choose between them in terms of absolute, in absolute terms, as somehow having more reality or less reality. But, and you might think here of an analogy to the cosmic microwave background frame. That is, although we think we live in a relativistic universe, and that would lead us to think that, well, there's no metaphysically privileged way of slicing up space-time. Nonetheless, there are certain ways of slicing up space-time that seem to be pragmatically useful or are suggested by contingent facts of our world, dynamical facts about our world, like the rest frame of the cosmic microwave background. So an analogy to that sort of idea, he says, well, although there's nothing metaphysically privileged about any particular basis, there are dynamically preferred bases. That is, decoherence effects are going to pick out a basis, at least approximately, as being pragmatically preferred. So the right basis for beings like us. And according to David Wallace, the way he puts it is that the Everett interpretation just is quantum theory interpreted realistically. So it's the bare theory, but the problem with the bare theory, according to Saunders and Wallace, is that there wasn't enough details of how quantum mechanics actually works. That there wasn't enough dynamics, there wasn't this understanding of decoherence, and in fact we have all the resources we need within quantum theory without adding anything, without adding these extra minds, these extra worlds, to recover our experiences of, our definite experiences of the world. And 20 years later, David Wallace, he finished his physics PhD and then wrote a dissertation with Simon Saunders, and you can sort of see his book that I'm sure most of you are familiar with as the sort of canonical version of his view. So the origins of this approach are within certain technical developments, namely the decoherent histories formalism. So I should probably say something about this. So the idea of decoherence is that when you model more than just the quantum system you're interested in isolation, when you include the environment, possibly the entire universe, you find that interactions between the system and the environment, unitary interactions, lead to the delocalization of interference terms, such that when you restrict your attention to the object system, when you take the reduced density matrix, tracing out the environmental degrees of freedom, you get something called an improper mixed state. That is, a state that looks very much like a mixed state, which you can in effect treat as if it's just a sum of one-dimensional projections with some constants out front that are apt for interpretation as epistemic probabilities. But we call this an improper mixture because the interference terms are still there, very, very small, but non-zero. So the sort of histories were interesting for Everett are these branching histories. So maybe I'll talk about branching histories and then see about decoherence. So the idea of a history is that I can specify a family of projection operators at some time. But I can also specify a family of orthogonal projection operators, mutually orthogonal, and summing to 1 at a later time. And I can define a history by picking out one of these projectors and then evolving the state forward unitarily, picking out another of these projectors, and I can refer not to the I can pick out a history just by the indices that I attach to these projections. Actually, I'm confuse my notation. So it's just A1, B1. And so if I have a branching history space, then I can take all my histories to overlap, in which case they would be one stem, and then by picking out different projections in this sum, I can take myself along different branches of this collection of histories. And branching means that when I pick out a history here, sorry, hopefully this was clear that time is going off the board. When I pick up a history here, I can forget about the past of this history. They all agree up to here, and then I only need to concern myself with projections that take me further along the branches. And the condition on the histories is called medium decoherence. That's necessarily sufficient to get a branching history space. So I think for time's sake, I won't go into the technical details. So the idea is that decoherence only relies on unitary dynamics, given by the Schrödinger equation. If decoherence gives us what we need for branching, then nothing needs to be added to the theory to get branching worlds. Proviso, for all practical purposes, we still have to worry about these improper mixtures, these off-diagonal terms. That is, there's negligible but non-zero interference between histories. Yes?
Sorry. I heard that Gell-Mann and Hartle has its own interpretation of their formalisms. Is that correct? Or they were just implying this Saunders Wallace interpretation. I don't know if there are two interpretations within the same interpretation.
Yeah, so this is a sort of technical formalism for dealing with unitary quantum mechanics, which works perfectly well independent of any interpretation, and it's a matter of what significance you want to give to, say, the non-experienced branches or something. But as they present it in this 1990 paper, it's as in conception an Everettian formalism, and the reason they give for developing this formalism is for cosmological applications. So one problem that I haven't mentioned by concentrating on Stein is the idea that, well, if quantum mechanics necessarily has to leave an observer outside the system, there's a problem with describing the whole universe. How do we get anything meaningful if the only results from quantum mechanics that are relevant are experiments performed by an observer? That's not a very good cosmological theory. So yeah, I mean, in attributing all this to Saunders and Wallace, there's definitely room to object that all they're doing is precifying work of physicists, and they're very careful to attribute these results to the physicists. It's more the sort of conceptual, stuff that they take on, as I'll explain. So I think the sort of philosophical questions that you might have relevant to our concerns here, at least when we thought we had a basis we were concerned with, we thought we had relative states, we had no doubt about what the relative state of the observer was with respect to the measured system and vice versa. But with these non-zero but negligible interference terms, we've got approximate orthogonality. We're left with these questions. Well, not very nothing very surprising. Why are decoherent histories relevant to our experience of the universal wave function? Remember, Saunders said that there's nothing metaphysically preferred about any way of chopping up Hilbert space. And secondly, why is our experience confined to a branch? If there's negligible but non-zero interference, that doesn't necessarily mean that we shouldn't experience other branches. And so these were questions that the Saunders and Wallace were concerned with. So going back to Gell-Mann and Hartle, they introduced this notion of an observer as an informational gathering and utilizing system, IGUS. And a similar idea is in Everett's original paper. He talks about these machines that have records, and we can take them to be models of observers. But there's this evolutionary explanation that appears here that Everett doesn't seem to have introduced. So the reason why systems such as IGUSs exist, functioning in this fashion, going around, recording results, using them to do things, is thought to be sought in their evolution within the universe. They're not just machines, they're evolved beings. It seems likely that they evolved to make predictions because it is adapted to do so. The reason, therefore, for their focus on decohering variables is that these are the only variables for which predictions can be made. The reason for their focus on histories of a quasi-classical domain is that these present enough regularity over time to permit the generation of models, schemata, with significant predictive power. So here, there's the idea that if we're going to make predictions in a branching universe, we're going to have to do so with respect to this quasi-classical domain of decohering branching histories. So Saunders sort of takes up this theme and argues that there are some necessary conditions for the evolution of complex life like us, that when we think about what they mean in this context are sufficient to cause medium decoherence, which is sufficient for this branching structure. So he says the metabolism of a complex organism requires timescales much longer than decoherence. Well, that seems true. What we know about decoherence, what we know about complex life, decoherence takes place on vastly smaller timescales than, you know, thinking of something like even the species present a fraction of a second. The structure of a metabolic process, including processes like replication, is encoded in the evolved system somehow. It's physical encoding in the IGUS. Any encoding of information has finite complexity. We're finite beings. Seems fair. The metabolic process is stable under small perturbations of structure. If it weren't, we wouldn't have a very long life. Very small perturbations of structure were sufficient to lead to the end of the metabolic process. Then presumably we will make it out the door in the morning. And then he says to be most fit, an evolutionary adaptation is encoded with minimum information content. So this one, I think, if we look at biological evolution theory, well, there's redundancy in the encoding of adaptations in our DNA, and there's this phenomenon of entrenchment. So maybe that's a bit doubtful, but you know, let's just grant it. Well, what do we have? So those were necessary conditions for life like us. So we've got something like a transcendental argument. So if there is complex evolved life, then necessarily 1 through 5, these are preconditions for the possibility of a complex life, at least evolved complex life. Saunders shows that his interpretation of those 5 conditions is sufficient to force medium decoherence, sufficient for this branching structure. Well, look around you. What do you see? Complex evolved life. So we can conclude, if this is an Everettian multiverse, then the necessary preconditions of evolution of complex life, the fact of a complex life, means that there must be this quasi-classical domain that Gell-Mann and Hartle referred to, this domain which some in some sense, we evolved to occupy. So this is all well and good, but I suppose, well, this is also a sort of way to try and motivate Wallace's intervention. The worry of empirical incoherence is that in an Everettian universe, we would not have definite experiences, though we would falsely report otherwise. So the existence of this quasi-classical domain that we occupy is all well and good, but it doesn't quite tell us what we would experience in such a universe. The problem of empirical incoherence is something like, if Everettian, then we don't have determinate experiences. Just to put it simply, so contrapositive, if we have determinate experiences, then we don't have an Everettian world. So there's more complications to get in the empirical incoherence, but something like that is going on. And if we've shown that there's this quasi-classical domain, this branching history structure, we haven't quite said anything about whether or not we have determinate experiences, or whether we falsely report determinate experiences. So this is just what Saunders takes to be a sort of synchronic argument that I've given, that just looking around us right now, seeing complex life, we say, well, there must have been some kind of decoherence at some point. But we also want there to be diachronic consistency over multiple times. And to get that for ourselves, to sort of reach this sort of continuity through multiple branches of a history, Saunders considers two strategies. So predictability we already heard about, but he also focuses on this reliable production of records, of memories. And he says the following: it is highly implausible that such records can in any sense be available to the automata, that is, the records that perhaps we could set this up better, the records that Gell-Mann and Hartle talk about, which correspond to projectors of the entire world. Given that the dynamics is dissipative, the projections will concern radiation propagated over vast regions of space. What is essential is the possibility of records incorporated into the automata themselves. But, and this is to sort of set up a worry that that Zurek and quantum Darwinism is going to set out to solve. If there's no external record of what you are remembering, if the record is just in your brain and there's nothing outside to which it refers, perhaps you might worry that there's the same kind of radical deception going on. Namely, we've got this record in our head, we falsely believe that there's this determinate measurement result, but there's nothing out there in the world that our record, that our memory corresponds to. Okay, so that's sort of flagging something for later on. I want to come to Wallace because I think this is where we find a genuine attempt to argue that our experience must be confined to branches in an Everettian, even in this emergent Everettian branching structure. So this is the other paper that I recommended reading. So, in Wallace's account, ultimately observers are going to be dynamical patterns of the universal wave function. So his inspiration here is Daniel Dennett's real patterns, which is an argument for the reality of mental states. And from there, Wallace takes the idea that this that higher order ontology, facts about observers, even tennis balls, chairs, tables, cats, what have you. What it is to put that sort of object into your ontology, to say that this is something that exists, this is something that's real, is to say that I accept a theory that is very useful, that refers to those objects, that leads me to believe in those objects. So the predictive and explanatory power of theories I accept, which make use of those objects, which enable me to do useful things, predict and explain, that is sufficient for me to say that object has reality. So this is also an approach which was taken by Ladyman and Ross, called by Don Ross, rainforest realism, to take this specific application of this idea of real patterns and generalize it to our ontology in scientific context. Here it's useful for Wallace because as Democrats, I'm not sure how many people are familiar with Plato. It might be worth just saying something about how he sets it up, because he has this neat thought experiment or intuition pump in his phraseology, which is taken from John Conway's Game of Life. So their thought is that we have a very, very simple universe. It's two-dimensional, it's discrete, and it's
Tom,
just...
You're looking at the clock, right?
We've got 5 minutes.
Yeah, well, we started a bit late, okay.
Yeah.
I'm just looking at all the dots up there.
No, you're making a good point. I should not make more dots.
We can go like 5 or 10 past.
Yeah, sure. Yeah, unfortunately, it would be nice to get to the newer stuff. Okay, so perhaps you're already familiar with this, so maybe we can speed through it. So the nice thing about real patterns for Wallace is that they can tolerate noise. They can still be there, and sort of scaling up the noise doesn't necessarily make them less real. They can also be temporally extended. So the example I was going to show you can sort of trade precision for explanatory value and large-scale predictability by looking at structures that have some sort of temporal stability, but they're definite. So Wallace then makes the following move. Cats are, so considering Schrodinger's cats are by definition patterns that behave like cats. So we should identify those with the two such patterns in the superposition. The relative states each refer to a cat. Those are each patterns that behave like cats for the observer in that relative state. And he says that while we can have a superposition of patterns, it makes no sense for a pattern to be a superposition. Okay, so the same thing applies to observers. So let's at least get this Zurek stuff on the table. Sorry, I actually thought I had another half hour, but of course I don't. Sorry. So one of the things that Wallace says, that if we think about what sort of pattern an observer is, an observer is not superposed but duplicated by the measurement event. We're regarding mental states as special sorts of patterns. These patterns are more likely to be behavioural patterns than visual patterns, patterns in the visual cortex or what have you. Well, there's a difference between the behaviours associated with falsely believing oneself to know an outcome and genuinely knowing the outcome. Now, of course, this difference may not be relevant. You may not try and corroborate the outcome, but if you do, when you genuinely believe, you'll confirm your belief, and so on and so forth. So this was my attempt to try and motivate this worry of Zurek that it's not enough just to have records in your head. An observer, when they go to check the result, is only going to be able to check some part of the environment. Having this projector representing the record on the entire world is not much good to them, and they should be persistent. So the idea of quantum Darwinism is that if we're going to have objective results, we need to do more than just think about the system when we look at decoherence, when we just trace out the environmental degrees of freedom. Rather, we should consider subsystems of the environment, and the sort of condition for objectivity that he considers is going to be one in which fragments of the environment, subsystems, have enough information to reconstruct the state. So they, in a sense, contain records of the state as well as the system, particularly if the system is the observer. So he calls this requirement that multiple subsystems know or have information about the state of the object system, quantum Darwinism. So the idea is that the environment selects pointer states of the system. These are the states stable against decoherence. If you're in a pointer state already, you stay in that state. If you're not, you decohere into a mixture of pointer states. And the requirement of redundant records means that the states have to be copied throughout the environment, reproduction. So we've got selection and reproduction. So why Darwinian? Well, according to Darwin, natural selection is the result of, or speciation is the result of variation within a population, having heritable characteristics that are subject to differential reproductive success, selection, and speciation is the result of this process over geological time scales. So how does that work in quantum Darwinism? Well, the population would seem to be these environmental subsystems. What's heritable? Well, the quantum states being sort of copied throughout the environment. And what's the selection? Well, it's whatever is being dynamically picked out by decoherence. So I guess I'll end on this slide. So you might see a strong analogy or inspiration of Ravelli's relational quantum mechanics in this suggestion of Zurek that all quantum systems are potential observers in the sense of having mutual information. You can use information about or knowledge of one to infer about the state of another. And in quantum Darwinism, information about other systems is just stored in the system's quantum state. There's nothing special about quantum observers at all. They just see systems like qubits having information about other systems. So you might persuade yourself that there's something that gets you out of an Everettian picture. But everything here is unitary. These requirements of objectivity, nice though they are, if you take the quantum state to be the relevant object of quantum physics, you don't get unitary for that. You only get unitary. Sorry, you don't get objectivity for that. You only get objectivity relative to this decoherence process. Now, the decoherence process that is picked out by quantum Darwinism is different. It's a more stringent condition on the sort of history that you're prepared to accept. But perhaps the best way to see that, rather than as a competitor to the Saunders-Wallace view, would be a potential refinement. You could see them as simply saying, well, perhaps a more refined history space is the one that's relevant for an Everettian interpretation, if it's to not just secure records for the observer, but make sure that those records correspond to records in the environment. So we haven't done anything to break the superposition. What we've done is just introduce new requirements that ensure consistency between environmental subsystems. So just more requirements on what we're prepared to accept as a valid branching process. So I just stop there. Thanks. Sorry.
It's okay. Should we just do questions for a couple of minutes? So
Yeah.
people-
Yeah, I was hoping that we were going to have a long discussion, but obviously not.
Let's just take a couple, yeah.
This is kind of a broad picture question about what do you think. So for me, it's a little bit, maybe not. It sounds like a lot of anthropic reasoning here, like an anthropic principle. And I was wondering if you have any thoughts about someone who follows up an approach like this, where that person has to say that biology and quantum mechanics have to keep separate, or where you think, like, for example, if you were to say that biology could be reducible in some sense to quantum mechanics, then I am afraid maybe many of these arguments here are going to be circular, just because you are using some biological facts to motivate some things about your quantum mechanics stories. But if then biology is going to be reduced to quantum mechanics, then maybe I'm not completely sure, you may have like a circularity worry. Yeah. So I don't know what you think about this relation between biology and quantum mechanics, and how fruitful you think it's going to be.
Yes, I mean, I take Wallace to be trying to actually circumvent that potential circularity by saying that what we're interested in are real patterns, and those aren't going to be patterns in a quantum state unless it's subject to decoherence. So I skipped this slide, maybe come back to it. So he says these patterns that we take to be the real things are somehow, by definition, by necessity, definite. And if we want to get out some definite structure from quantum mechanics, well, without the specification of some set of preferred operators, this space is structureless. We can only say, this abstract statement about what kind of mathematical object it is. It's only once we have some sort of basis that we can do something like, give a probability current in space or something like this. So I take Wallace to be, through this appeal to real patterns, doing something like saying, well, yes, quantum mechanics is relevant for understanding biological processes, but biological processes are just going to have to be found relative to to some decomposition of the state on a basis.
I was just going to ask quickly about the Stein stuff. So it seemed like he wanted to say a requirement for physical theory is that you can schematize the observer within the theory. I was just wondering, maybe your own take, or from what you know, what Stein would think, like, it must be then that physical theory is somehow special, because we don't think that, like, the theory of stock markets has to be able to schematize, like, observers within the theory. So you might say the difference with the physical theory is that a physical theory is supposed to encompass everything, and observers are physical systems. But then that's just the usual reason that's given for why we should be able to model observers in physical.
I mean, that's a good point, and you might perhaps think that it's actually spatiotemporal theories that are the sorts of things that we're going to be able to pick out experiences, because our experiences are spatiotemporal. So maybe it's no surprise that Stein has trouble with quantum mechanics. But my interest of bringing Stein in was that I think there's actually it's hopefully going to be the payoff, but I've run out of time. That there's a responsibility to represent our experience of quantum phenomena, not just classical phenomena within quantum theory. And quantum phenomena tend to be discrete. You know, when we experience an interference pattern, what we experience is a series of discrete events that come to build up an interference pattern. And I think that's actually a problem for, well, potentially a problem for these sort of approaches that say continuity is actually hidden continuous evolution of accounting for the distinctively quantum features of experiments that we experience.
Why do you think, though, that we need to be able to represent our stock market experiences within our theory of the stock market?
Right, so yeah, should it be a necessary condition for a theory to be about something that we can represent observers within it? Perhaps not. So I think it definitely makes sense for spatio-temporal theories, and I think, yeah, I'm not sure where the cutoff lies, but I agree that there should be a cutoff. Not every theory needs to be a theory of the observer.
And with that,
Yes.
should we go to lunch? Dinner?
Excellent.
Thanks.